Hello, I'm Philip Zucker. I've been invited to give a short tutorial on satisfiability modulo theories, a topic that I find very interesting. You can follow along at this link, which is a Colab Jupyter notebook. This whole presentation is done inside a Jupyter notebook, so I can show some working examples and things. So an overview, what is an SMT solver, a satisfiability modulo theory solver? Well, it's gluing together domain-specific solvers using using a satisfiability solver algorithms. So satisfiability is very effective for these Boolean propositional problems, but you want to have baked-in smarts about reals and linear inequalities and maybe polynomials and notions of arrays and notions of bit vectors, and so you can have those in there as a higher level modeling language and higher level solving capabilities, and that's a SMT solver. So SMT solvers have many applications. I'll go over a couple of them. Then I'll discuss a bit of the guts of what an SMT solver is in a little more detail. And then discuss a bit about how egraph rewriting, equality saturation, the optimization problem that a lot of us are interested in SMT are related. And I can use SMT solvers to get some interesting capabilities, some interesting egraph capabilities. Okay, so a demo. First off, just like I think basic idea, first thing to sort of see what these things can do for you is that they're a solver. You can use them to find stuff. So here I'm using Z3, which is a popular SMT solver. In particular, I'm using the Python bindings of Z3, but there are bindings in many languages. And here I declare three integer variables. I make a solver. I say that I have the constraint that x plus y plus z is equal to 10. Then I ask it to check if that constraint is satisfiable or unsatisfiable. If it is satisfiable, and in this case it is, you can ask for a model, an actual solution. So if I run this, it actually finds stuff. And if I change these things, I get different solutions. I can add more things that x has to be greater than 3, and I'll get, or z is greater than 3, and it'll give me different solutions. And if I want y is greater than 4 and x is greater than 3, then actually it'll say unsat. Actually, there isn't a solution that has all these properties. So that's the basic idea. You can also use the command line. This is SMTlib. It's a textual format that these solvers take. And it's very similar. It has an S expression like syntax. You declare your constants, you assert constraints you want, you call checksat and get model, and there's a website and spec document describing these commands. And then you can call Z3, for example, and it'll get you a solution. But also CVC5 is another popular SMT solver, and it will take in the same file and also give you a solution. Okay, so that's how you use it to find stuff, but a lot of the time actually you're trying to sort of, the good thing is to not find stuff. The thing you're asking it to find are counterexamples to theorems you're kind of hoping or think are true. So here we're going to prove a very simple theorem, in the sense of there are no counterexamples. And the theorem is that for 32-bit bit vectors, the OR of a bit vector with itself is equal to itself. Okay, and so we negate that. We want to find something that for that property that doesn't hold. And if we ask it to check it, we get unsat. Okay, and Z3 actually has a convenience function for this, Z3.prove, which is just a wrapper of exactly those calls at the Python layer. And then what happens if you want to prove something that isn't true? So here is a theorem that would be true over the integers, that x plus 1 is greater than or equal to x, but in fact is not true over bit vectors because of wraparound. And so you get a solution here, but if a counterexample, so this is bad, this theorem is not true because I got a counterexample, but if I do that to make an integer, it comes back and sat. That is actually a theorem in the integers. Okay, so I'm going to go over three sort of usage categories of SMT solvers: constraint satisfaction problems, theorem proving, software verification, and synthesis. These are sort of related topics, and it isn't. We're using an SMT solver for all of them, so maybe the difference of these categories is gray sometimes. But for constraint satisfaction, it's really like things where I'm really interested in the model and getting a model is good, and the model like has a solution in it that I actually want to use to do something. So things I put in this category are solving Sudokus, N Queens puzzles, the Sen plus more equals money puzzle. If you've seen any of these, you've probably seen Sudoku. But then more useful practical things that aren't just puzzles are things like graph coloring, which is related to register allocation, scheduling problems, dependency resolution of package managers and things. You need, all the versions of stuff you need are these constraints, and you can ask solvers to give you versions that meet all the various constraints of all the different packages. You can also use Z3, interestingly, to solve compiler problems. I said graph coloring, scheduling could be instruction scheduling in particular. And there's a really cool project, Unison, which made an LLVM backend as a research program, research project that could solve interesting compiler backend problems using constraint programming, very related to SMT. And I believe there's also a lot of work kind of going around right now about making super powerful ML optimizers for GPUs and things. There's a lot of money in solving those constraints really well, so maybe using a constraint-based approach is interesting there. Another use case is theorem proving. So theorem proving is interesting. You can do it on a computer. You can do it where the computer is checking your moves. And there's popular systems like Lean and Rock and Isabelle and Agda and so on. And these systems, by default, are fairly manual. I guess I'm talking about interactive theorem proving. They're fairly manual. And so there's tactics that can do more automation for you. And many of these systems have tactics that reach out into SMT solvers, have the SMT solver figure something out that returns something back to the interactive proof assistant. And the proof assistant somehow chews on a proof or reconstructs a proof out of the breadcrumbs that the SMT solver has given it. Or maybe you can just trust it is also a thing you can do. You can just trust the SMT solver is right and not re-extract a proof out. A system that I've been working on that I'll take a few moments to talk about is Knuckle Dragger, which is also a proof assistant. It's a LCF style proof assistant for the SMT lib logic. So it's intimately integrated with Z3. In fact, the Z3 Python bindings are the syntax, are part of that is how you construct Knuckle Dragger formulas. And really, the idea is starts from the thing I showed earlier. There's a Z3 convenience function called prove. Well, I wrap it. So instead, I change x to an integer, but I need it to be a bit vector for that to be an actual theorem. So you can state a statement, you call prove on it as you would just a single Z3 shot, and it'll give you back sort of a certified object, a proof object, that then you can use in further proofs, which you can give the solver access to by parameter. You can list other ones of these you had previously. Or there's also sometimes Z3 is not so great at, it's not a complete solver for full first order logic, or many of the things you can express into the language of Z3, it really has no chance or capabilities of being able to solve. But a big step towards that is the ability to manually instantiate quantifiers, which is one place where the heuristics of Z3 can sometimes do very well, but sometimes can get tripped up. And so then you can have more interesting theorems, like here is a theorem from Zermelo-Frankel set theory. It's the theorem that not all classes are sets. It's sort of a version of Russell's paradox, the set of all sets thing, but stated as a theorem. And so you need to unfold some definitions. These are tactics manipulating a proof state object in all regular Python. And you can unfold some definitions. You can introduce stuff into your context. You sort of crucially need to give it the Russell set, this or this class that really can't be a set consistently. And you can extract out Skolem constants and things. This is a little hard to follow. Maybe not the prettiest thing in the world, but the point I'm trying to get across is that what Z3 on its own would have no chance of doing this because there's just too much quantifier stuff going on, and you can manually lead this thing through in the case you do. So it's sort of a way of starting at all the things Z3 can do and slowly pushing it out, giving you more capabilities if you're willing to put in the work to explain something to the system. And it is checking every step of the way using logical principles. Okay. So another big usage of SMT solvers is is software verification. And that can include symbolic execution, bounded model checking. These are sort of the same thing. Some interesting systems are CBMC, Connie. CBMC is the C bounded model checker, so you can do its actual regular C programs, and it'll unroll the loops in them and symbolically execute them, throw them into a SAT solver and SMT solver, do some choices of that in the back end, and try and find places where there's buggy bits or things that fail assertions. Connie is a Rust version of that, basically. CLE is a symbolic executor for LLVM, maybe less, more for, the symbolic executor for LLVM. Alive is a really cool verification tool for the LLVM and IR trying to do translation validation. F star and Daphne could have been in that category above of theorem proving also, but they are theorem proving / software verification systems that discharge a large majority of their obligations through SMT solvers, in particular Z3. And here's a project I've been working on, ASMC, an assembly checker based on Ghidra P code, which is it's a decompiler framework made by the NSA, released as open source, and has a ton of instruction set semantics in it that get lifted up to a common representation. So I can support a bunch of different assembly architectures. And what you can do, there's different ways of using it. So you can use it as a Python library, ASMC, but also you can annotate with these regular GNU assembly macros, basically SMT-lib statements of SMT-lib statements describing pre and post conditions, things you're trying to check. You can make it, you can compile it. Again, there's different ways of doing it, but one is a command line tool. You can run this. It'll execute it. This is describing all the P code execution stuff. And in this case, the verification condition fails because of an aliasing problem for this swap routine is what this is. It's swapping the memory pointed to by RDI and RSI by putting in the temporaries. But if there's an aliasing of RDI and RSI, this thing doesn't work as you would expect, as you might hope it does. Okay, so now we can talk a bit about SMT guts. So logically speaking, what is SMT doing? It's finding a model for a logical formula. So I just want to put these symbols on this page. It's this double turnstile. M is a mathematical object that there's a relationship between mathematical objects that obey particular formulas, and is finding those mathematical objects. I want to talk about SAT solving, at least briefly, because it is the core of where SMT is coming from. And yet I also want to de-emphasize it a little bit because I think that a lot of descriptions of SMT solvers spend a lot of time on SAT. For good reasons, but we'll go over very briefly. So SAT solving is a triumph of automated reasoning. They've made tremendous strides even since the revolutions in the 90s. So I just want to show this little chart here, which I think is really cool. This is all the SAT competition winners from all these different years, 92, 97, all the way up to 2024. And I don't actually know exactly what these numbers mean, but the point is that like even the algorithmics, these are all in the same computer, a modern computer. Even the algorithmic heuristics and so on have improved like significantly over the last 20 years, even beyond the revolutions of transitioning to the the conflict-driven clause learning paradigm, uh, which we'll get to in a second. So set solving, like simply speaking, I like to describe just run. It's the ability to run a circuit backwards. You're trying to guess an input to a circuit that makes the output true. In particular, the input is in conjunctive normal form, is sort of this nice normal form to be working in, which is it's a giant and of ors of possibly negated literals. And the basic method for sat solving that is dominant for sat solvers is you're doing some search, like you branch every once in a while, like just saying like I'm gonna guess that P is true, and then maybe I'll guess Q is false, and I'll guess R is true. But in between all of that, you're also doing propagation because sometimes, like once I know R is false, actually I know Q has to be false with that's unit propagation. Um, so it's interleaving search and propagation plus piles of heuristics about which variables you should try and pick first and whether you should make them true or false. And you do that by collecting bits of data about them and stuff. But also a big revolution in stat solving occurred with the idea of conflict-directed clause learning, which happened in the 90s. And what happens then there is an older style, the straight DPLL style solver is just sort of backtracking search. But instead, conflict-directed clause learning, when you hit a conflict, once you've like taken some guesses and like gone down a wrong alley, it learns a new clause by doing resolution on the input problem to derive a new true clause, and then it adds it into its clause set, and that clause will block the thing via propagation from ever going down into that bad corner ever again. And so this lets you sort of jump way back jump, instead of like a little bit of backtracking. You can jump way back, and it might also change the whole way your like search proceeds. And it's been a very effective idea. And there's just a whole pile of technology and things to say about sat solving. Maybe I'm not the person to say them, but it is a field unto itself. And the sat solvers are ridiculously powerful. Okay, so then SMT, what is that? Well, you want to have a higher level stuff you want to be able to talk about. You want to be able to talk about integers and other things. You don't have to, like, as a modeling language, CNF is not great. It's a nice intermediate language in between what the solver implementer needs and like what a problem generator needs, but it's not that pleasant. So SMT is like higher level. And there's two sort of styles of doing it. Pretty dominant these days is the lazy style, but just to mention the eager style is you compile eagerly your entire problem into sat. So like if you know you're doing this problem with integers, but you know all the integers are between 0 and 100, then like it is a bounded problem. You can describe each of those integers with a bit vector, and you can bit blast them. You can bit blast bit vectors, just like rip it apart into its component booleans and throw the whole thing into a sat solver, and that's the thing you can do. An interesting technique I just want to mention briefly is Ackermannization. So you can encode congruence closure into sat, because if you have only, I don't know, 20, 100, 1,000 terms in particular you sort of care about, you can consider the equality of all those different terms, and you can encode the congruence closure into a clause that goes into the sat solver. And all the different equalities you can talk about are sort of these opaque booleans, sort of. Once you have, like, you can eagerly encode what the congruence closure would do logically just into the sat solver ahead of time. But then there's lazy solving. So you can abstract theory propositions as opaque P's. And from the sat solver, it's just a P and a Q and an R. It doesn't know that it's talking about equality or it's talking about inequality or whatever. And then the very lazy version of this, you could just run a sat solver, like you get that model back, and then you check it with all your theory solving stuff, and it's like, oh no, actually that doesn't work. There's actually sort of a secret clause that the SAT solver didn't know about before, and so you add that into the clause set that the solver has. You run it again, you get a new model, and so on and so forth. What a more tightly integrated actual production SMT solver is interleaves the theory reasoning and the SAT reasoning. They're just more tightly coupled than that. And so, I talk about SAT propagation, unit propagation. There's also theory propagation that'll force certain literals to become true, and the theories are like exchanging values with each other and things. And we're going to talk about that in a second. Okay, so theories, what are they? Theories, in my mind, they usually just mean they're kind of like a black box solver, and a black box solver that like, to be black box means that there's some like API surface that somehow is like modular, and you don't really need to know what's inside the solver, but there's this modular interface and the things can plug together. Also, mathematically, the word theories often refers to a set of formulas. The deductive closure of the axioms of the theory is like the set of formulas theory that sometimes you're talking about mathematically, but for my purposes, I'm usually talking about theories as a black box API. So what is this interface? One way to get a good feel for what this interface is to look up what user propagators are. So there is like the ability to bring in a user theory into Z3. I haven't really used this that much, but it exists and it is documented. And so theories need the ability in SMT to be pushed and popped because there are decisions being made that need to be backtracked eventually. So the SAT solver notifies theories of like when they need to push and when they need to pop. So it needs to maintain some kind of stack, something like that. The theory needs to be notified of all sorts of different events. It can register for different events that might be happening. So if a term is created that the theory might be interested in, the theory should be notified of that. The theory might depend. I mean, it all depends on like how you organize your code. The theory might have to create fresh constants. It might be responsible for that. It might be informed that a particular term has been fixed to a particular value. It might be informed that a decision variable, a propositional variable, has been set to true or false. It also, crucially, and this is sort of some of the meat of it, it needs to be informed of equalities that have been learned and disequalities that have been learned or propagated to or decided upon. And then it also should have the ability to propagate out things from inside of it that it can learn and spit out sort of these same things that it wants to be informed of. And the things that should spit out are equalities, disequalities, and also just like the literals, the propositions it's in charge of, like whether that it thinks that now has to be true or that has to be false. In order to work with CDCL, it also needs the ability to explain why the theory doesn't think something is possible. And explain is it needs to just say a small set of literals that have been asserted to it that like mutually can't be asserted that way. Likewise, it needs to explain if it propagates equalities out, why it, like what other things like happened to it previously that like made those equalities get forced. And there might be a bunch of stuff going on that's like irrelevant to like the actual problem or conflict. And so it's sort of the theory's job to like figure that out in order to participate in CDCL. So some example theories are atomic equality, just A equals B, and you can do that with a union find. Uninterpreted functions is basically the egraph. It's the thing that does uninterpreted functions, and sometimes this is called UEF. EUF, sorry, equality of uninterpreted functions. There's arithmetic, and there's also a bunch of like sub-theories that have like very special solvers, very special forms of arithmetic statements. So one thing that has propagation behavior is intervals, like intervals that are like connected to each other. It's saying that x is less than 7 but greater than 4. These things, there's propagation due there. You can also have linear equalities that it needs to solve, and it could like, if you assert a new equality, it could learn a new equality that sort of wasn't obvious unless you know about linear equalities, and it could spit that out. We'll talk about that in a second. two variable inequalities, difference. This is called difference logic. That particular form has a nice algorithm of shortest paths in a graph. You can encode like the smallest bounds on these things as the shortest path in a graph. So there's very fast algorithms for that. More general linear inequalities, you can use the simplex algorithm to, again, figure out if they're infeasible or learn new equalities to spit out other stuff. I just want to know that tractable theories often also show up in abstract interpretations, because you want theories that have like good propagation, and in some sense you're describing sets of solutions, which is what abstract interpretations are also doing. There's the theory of bit vectors, which is extremely useful, and it can be bit blasted, and sometimes that's the right thing to do, but also there's reasoning that happens like at the more abstract level of reasoning, rewrite rules that apply to bit vector identities. There's crucially also the theory of arrays, which is really a theory of first-class functions, but sort of a different kind of first-class function than a more somewhat limited notion, a little bit limited notion of first-class function compared to what you might have in scheme or functional programming or something. There is support for lambdas, but your mileage may vary. They can evaluate them, but it's not doing. Lambdas can encode very difficult problems, and you're sort of on thin ice there a little bit. There's a theory of algebraic data types. There's also a theory of sequences, finite sequences. Okay, so theory combination. How does it kind of work? There's two. The big one is Nelson-Oppen, and then there's also Shostak, which is maybe a little rarer and maybe I understand it a little less. So Nelson-Oppen combination. The basic procedure is, you have some constraint you want to talk about, and you purify it. You want to separate it into pieces that are going to go off to different theory solvers. So purifying is you flatten the thing, you generate a bunch of fresh constants, E1, E2, E3, E4, and you can flatten a compound expression by giving names to the intermediate expressions. And then you can filter and be like, well, this one's just sort of a regular, this one probably go into any theory, but let's say it goes into uninterpreted functions. This is some uninterpreted f that goes into the uninterpreted solver. This one is talking about linear arithmetic stuff. This will go into the linear arithmetic solver. The less than or equals 2 will go to linear arithmetic solver. So we have this, we split it up into this uninterpreted function solver piece and this linear arithmetic solver piece. And then what you can do is you guess or find a working arrangement of the shared variables. So some of these variables go across. E2 appears in both, and E3 and E4 appear in both. E1 doesn't, so you don't have to show that one. But you want to guess, is E1 equal to E2? Is E2 equal to E3? Do they not equal to each other? So you need to guess or find a working arrangement, a assignment of equality or inequality to all the possible pairs of the shared constants. And if some theory says unsat for every possible arrangement, then the thing is unsat. And then if all the theories say sat, under the appropriate assumptions of the theories involved, these are mathematical assumptions, you can build a model out of the individual models. You can combine them into a total solution, and it's less obvious than you might think that is possible. So some theoretical words just to throw out there to talk about. Stably infinite is a term that gets thrown around. I think this is if it has a model, it has an infinite model. And I suspect this is a model theoretic way of saying it has a good notion of fresh, that you're sort of never like so constrained that you can't have a new fresh variable. And relaxations of this condition are possible. There are stronger and weaker conditions that a theory can have than stably infinite that might be useful in a combination problem. Convex means that the theory propagates equality well, basically, and non-convex means it doesn't propagate equalities very well. So I was talking about guessing or finding a working arrangement. in sort of the like typical way you think about Nelson-Oppen in the like golden path case, for some particularly good theories like linear arithmetic over the reals and uninterpreted functions, these theories are convex, and actually you don't need to guess the arrangement. It'll the propagation of the theories will find the forced equalities for you and the forced disequalities for you, and you don't need to guess anything. You don't need to do searching for this arrangement in addition. But for more general theories, there are many theories that are non-convex. So finally, egraphs and SMT. You know, egraphs are in Z3. Can we use it to do egraph rewriting or quality saturation stuff? Can we use it to optimize compiler IRs? Just some issues, notes, and some solutions to that. So the thing you want out of an egg-style system is you only want the equalities to happen that like had to happen, the justified equalities, the things that like were forced onto the system. But that's not the contract of an SMT solver. An SMT solver is allowed to give you any model it wants. And it can have more equalities than it strictly had to. That's fine as long as it just satisfies the equations you had. So if you only give me equations and no disequations, then a universe of a single object is always going to be an acceptable solution to that, which is just an egraph is completely collapsed into a single E-class, and that's not really what you want. But here we can see how basically the model being returned by the theory of uninterpreted functions over an uninterpreted sort looks an awful lot like an egraph, and it is basically a serialization of the egraph inside of Z3 back to the user. So these val zeros are the E-classes, they're the model values, and the constant A is an E-class 0, Y is an E-class 1, X is an E-class 1, and then F, this is kind of the E-node table of F here. But crucially see that, again, the contract of Z3 is it totalizes the function F. So it has this else clause, and things are actually more things are equal than strictly have to be equal. So, for example, we have F of A here. So F of A goes into this, that's 0, goes into this else clause. F of A is an E-class 1, but so are X and Y. So actually, even though it isn't forced to be true, that is what happened in this model. And you can help this somewhat by asking for the minimal model, the one that has the most disequalities. You might think it's the biggest or smallest maximal or minimal egraph. It has the most disequalities and the least equalities. So you can use the optimization mode of Z3 to sort of break some of these things that are just random equalities. But another thing you can do is you can do in that theorem proving mode, instead of asking for the SAT model, you can be sort of chasing unsat. And so if I want to know if X is equal to A in the minimal version, I'm sort of asking, are they equal in every possible model? Is there a counterexample model where they aren't equal? And we get SAT, so that actually that's a counter. There is a counterexample to that. So actually, that's not a theorem of these two starting equalities. But if I ask X is equal to Y, I get unsat. So I can actually determine the terms that need to be in the same E-class via these pushing and popping and asking these SMT as an oracle. And that's the basics. That's the basis for an interesting prototype for Egraphs modulo theories. Use SMT as an oracle for equality. You throw all the terms you're interested in, the terms that would start generating your egraph, into a set that you're holding at the Python layer or the metaprogramming layer. And the rebuilding operation records oracle qualities in an external union find. And then you can do bottom-up e-matching and an SMT query for egraph containment to do an actual quality saturation step. What's really cool about this is it supports all the stuff SMT or Z3 does from the outset. So you get an egraph that has intrinsic support for linear arithmetic, arrays, polynomials, and those don't have to be rules. That's just like Z3 has that built in, has decisions procedures built in for that. And you can also have a contextual egraph using assertions under implies. So if I can assert to Z3 that if A equals B, also f of x equals f of y. That's sort of a union assertion under the assumption A equals B, and you can query under different assumptions also as basically as theorems under those assumptions. So I have a blog post describing some of these, but I can also show sort of a demo. I've wrapped this out into a library in my knuckle dragger library. So here is just the raw term, the C graph for the raw term a times 2 over 2, this sort of related to this canonical egg example. And then I can just ask it to rebuild it, no rules. Z3 just knows a ton about this, and it immediately can simplify these things. And by asking all these oracle questions, I can figure out which terms are equal to which other terms. And so you get this thing that you actually know that this original expression is equal to A, and indeed you can extract it. The original term t up here, extract it, it is indeed equal to A. So here's a lot more resources on SMT. These are some of the ones that I pulled on to make this talk. Thank you.